And now we're moving on to the first part of Algebra 2's second unit, that is functions. This one's extremely general, but here's a topic-by-topic list of what this video will go over. We've got domain and range, composition functions, inverse functions, one-to-one and onto functions, end behavior, multiplicity, transformations, application of logarithms, and regression functions. First, we're going to define what a function is. Functions should pass the vertical line test, meaning if you had a vertical line going through every single x value of the function, left to right, the function should only hit the line once for a given x value. Now in this second example right here, we see that a vertical line is hitting the equation twice at a given x value, so it is not a function. Function should only have one y value for each x value. Now let's talk a little bit about a function's main qualities and characteristics. Firstly, domain is the set of x values for which the function produces some sort of output, or the x values for which it exists. Rational functions domains, specifically, can be found algebraically. Their domains are everything but where their denominators are equal to 0, which is when they're undefined. Now this fancy notation right here with this r with two lines just means a set of real numbers, and this line in between basically means like another stipulation to the rule, and we'll talk a little bit more about that when we get to probability. So in this case, if we have the function f of x equals x minus 4 over x plus 2, obviously this is going to be equal to 0 when x is equal to negative 2. So our second stipulation here is that x is not equal to negative 2. So the domain is true. The domain is true when we have the real number set, so we're in the real number set, the set of real numbers, and when x is not equal to negative 2. So the domain is all real numbers if x is not negative 2. Alright, now let's take a look at radical functions. Other rules for radical functions domains are functions like a square, cube, root function. These are all real numbers except when the radicand is less than 0. Alright, so here if we have the square root of x minus 5, this is equal to 0 when x equals 5 and less than 0 for all x is less than that. Therefore our domain is all real numbers greater than or equal to 5. Now let's talk about range. Range does not need to be found algebraically for the purposes of the Regents Exam, but it's just the set of all y values that the function is defined for. Now, let's talk about one-to-one and onto functions. One-to-one functions have no repeating x or y values, so something like a sinusoidal function like sine of x is not one-to-one since its y values, as we can see here clearly, are repeating. You could adapt the vertical line test to say that one-to-one functions must also pass a horizontal line test, where no point would touch a horizontal line twice. An onto function over here is pretty simple, just means that all x values have a defined y value, so just most normal functions. Alright, now composition functions may be new to you. They're basically just a function inside of a function put together, and here's how we write them. This dot, by the way, is a hollow dot. It does not mean multiplication, rather it means f of g of x. Alright, and I'll show you what I mean with this example. If we have h of x is equal to f of g of x, and g of x is equal to 3x squared, and f of x is equal to the square root of 9x, that means that h of x is equal to the square root of 9 times 3x squared. Alright, let's take a look at that again, alright? So we see how the 3x squared essentially just takes the place of the 9x inside of the f of x. That's kind of what we're looking for here, and here's just some work that would simplify that equation. Now we're going to shift over here, we're going to take a look at inverse functions. Alright, so when we've got an inverse function, they're pretty simple. They're basically what you get when you reflect any one-to-one function over the line y equals x. So let's just pretend that I'm a perfect drawer and this line is y equals x. When we reflect this thing here, y is equal to 3 to the x, then we're going to get y equals log base 3 of x. You can also solve to find inverse function by swapping the y and the x values of the original function. Alright, let's take a look at this. Let's say we have y equals 3x squared plus 5. We're going to swap the y and the x. We're going to get x equals 3y squared plus 5, do a little algebra, and we get the square root of x minus 5 over 3 is equal to y. And we use this notation here. It kind of looks like f to the power of negative 1. This just means inverse functions. Now we're going to switch gears and we're going to talk about end behavior and multiplicity. End behavior is pretty simple, and on the test, if you don't know what the end behavior of a polynomial is, you can just graph it. You'll see at the end of the functions will either go to positive or negative infinity, and that's pretty simple. But here's a quick trick to know. If the leading degree of your function is odd, like x cubed or x to the 5th, the ends will point in different directions. If the leading degree is even, like x to the 4th or x to the 6th, they'll point in the same direction. And if the coefficient of the leading degree is positive, like 4x cubed, for odd functions, it'll look like this right here, where we see it kind of looks like just like, y equals x, where we'll have, as we approach, as x approaches positive infinity, y approaches positive infinity, as x approaches negative infinity, y approaches negative infinity too. Alright, but if it's negative, like negative 3x to the 5th for odd functions, it'll look something like this other one right here, kind of in reverse, like y equals negative x. Even functions will have both ends going up for a positive leading coefficient and both ends going down for a negative one. Now, here's another thing. Multiplicity is basically just how many times something bounces. And we can see here as we go from 1, goes to 3, it kind of stretches a little bit, goes to 5, stretches a little bit more, we go to 2, it's kind of normal, 4, it stretches, 6, it stretches. And that's basically all we need to know about that. Alright, now let's go to a big topic here, transformations. It's usually 1 or 2 questions on the Regents, and if your teacher didn't get through them through the year, they're pretty simple, but the best way to understand them was some practice questions. However, here's a brief review and some really helpful acronyms that I used when I took Algebra 2 to remember function transformations. Firstly, there's 6 different types of transformation that the Regents wants you to know. That is horizontal translation, otherwise known as horizontal shifts, horizontal dilations, aka horizontal shifting or scaling, shrinking or scaling, reflections over the y-axis and over the x-axis, vertical dilations and vertical translations. Let's start with the horizontal dilations, translations, and y reflections first, and you'll see why in a second. Firstly, right here is the equation for a horizontal translation. You're going to take the equation f of x and you're going to basically make into f parentheses x plus or minus a. Again, parentheses is important. We're going to see why in a second. But let's say we had x squared, then a horizontal translation would be, we put the 4 inside of the x, inside of the parentheses, right? Alright, now this would be a right shift, right? A right shift because we subtracted that number a. Each point is shifted by some value a as we see in this graph here. So this point kind of shifts here, this point shifts here. Alright, now again, let's take a look at that formula right here. The change is happening within the parentheses. Within the parentheses, take note of that. And also realize that adding an a results in a leftward shift while subtracting an a is a rightward shift. Now let's take a look at dilations. Dilations shrink or stretch functions, and if we multiply them by some integer k, it'll get skinnier, and if we multiply them by some 1 over k, it'll get smaller. Again, this occurs within the parentheses as we see by our rule here, f of k of x, or f of 1 over k times x. Finally, our y-axis reflection is pretty self-explanatory. We take the red function, flip it over the y-axis, and you should have this background from geometry. Also, if you weren't already aware, the red function is the original while the orange or blue one are images. Anyhow, the equation for that is f of x becomes f of negative x. Again, inside the parentheses is where our change is occurring. Now we're going to take a look at some vertical stuff. It's all the same idea for a vertical translation, except adding an a moves it up and subtracting an a moves it down. Alright, so it'll look something like this. Now, this is different from what we had before. It is outside the parentheses. See how the x is unchanged inside that parentheses? Alright, it's not going to become like x minus 4 squared. It'll be x squared minus 4. Alright. Now, vertical dilations are essentially the same, except again the rule changes so it's outside the parentheses. So it's k times f of x and 1 over k times f of x. Alright. X-axis reflection is also similar. F of x becomes negative f of x, again outside of the parentheses. And we're going to flip over the x-axis. Now after all this, you might be wondering how on earth am I going to memorize all of this? Is just too much for me. Well, I got some simple acronyms for you. HIYA and VXVO. What do these stand for? We'll start with HIYA. It means horizontal inside the y-axis. Again, this doesn't really make sense, but when you think about it, any sort of transformation involving the y-axis, like reflection, and horizontal dilations and translations involves changing the rule on the inside of the parentheses. All 3 of those I just went over were inside the parentheses. Likewise, VXVO is vertical x-axis, vertical outside. All of these rules are going to happen outside of the parentheses. And you'll have to remember that translations always involves adding or subtracting an a, that dilations involves multiplying by k or 1 over some k, and that reflections involves adding in a negative. But that made a lot for me. I remember VXVO by thinking of the music company Vivo. Now, one last thing about transformations before we finish up with odd and even functions, regression, logarithms. The order matters. You always must perform your transformations in the following order: H, D, R, V. You can see what those stand for on my screen: horizontal translations, dilations, reflections, and vertical translations. If you don't do this, it'll mess up how your image is constructed. And I remember this by thinking helicopters do rise vertically. And you can make up your own little thing if you want, but that's just how I remember it. Alright, even and odd functions. A function is basically just called even if it is symmetric about the y-axis. So that's something like the cosine function of the function x squared. A function is called odd if it has 180-degree rotational symmetry about the origin, so f of negative x is equal to negative f of x for all x's in the domain. Right, so that's something like x cubed or sine of x. And you see this little fancy e just means like in, so all x's in the real number domain. Alright, 2 topics left. We'll go through these real quickly. Regression. This is different for everyone since we all have different calculators. If you have a TI Inspire, I recommend looking at our All You Need to Know for our Algebra 1 calculator guide. It's the same idea, same regression function. If not, just know how to recognize all these models. These 6 models here are very important, except for power functions, don't really show up very much, but those other 5 definitely important. And be able to use your calculator to find regression equations when you're given those data points. And applications of logs is our final topic. So we all know that this is the basic way to write a logarithmic equation right here, but here's some ways that that's actually useful and applicable in real life. And these may show up in word problems, especially on those 4-point or 2-point questions on your Regents. The first one is that we are going to show exponential growth and decay. So if we have this equation a of t equals p times 1 plus or minus r to the power of t, we can show exponential growth or decay by showing that p is our initial value, our start value, 1 is just a number kind of to represent like 100%, plus or minus, so minus is going to be a negative rate, plus is going to be a positive rate, and then our rate is always expressed as a decimal. So if we have something like 3% interest, right, that's going to be 0.03, and t is of course time. Now, compound interest can also be shown using this equation. The numbers mean the same thing except for n right here, which means the number of compounds per year. All right. So common compounding periods are monthly, quarterly, and daily, or yearly. It's how many times per year. We have 12 months in a year, 4 quarters, and 365 days, and of course 1 year in a year. So that would just be 1. Now, the last thing we have today is continuous compounding, which requires the use of the number e. And yes, it's the number e. It's a constant that's approximately equal to 2.72 and is the limit, if you know what that means, of the function 1 plus 1 over n to the nth as n approaches infinity. In other words, as this equation right here has n getting infinitely bigger, that's what that's equal to. And you don't need to know that. You just need to know how to use this equation right here when given a situation with continuous compounding.